predicting the relative boiling points of pure substances requires us to understand the different kinds of intermolecular forces that may be at play. So first of all, everything has dispersion forces. Dispersion forces come from the temporary dipoles, which exist due to uneven distribution of electrons throughout a molecule. So that's just any split second instantaneously, the electrons may not be uniformly distributed, so you get a slight difference in charge, but this is constantly changing. However, that will affect neighboring molecules, resulting in small intermolecular forces of attraction. Dispersion forces can actually get quite large depending on the size of the molecule, because dispersion forces magnitude is proportionate to the number of electrons in the molecule. So obviously some very large molecules can display some very large dispersion forces. But generally speaking, dispersion forces tend to be the least strong intermolecular forces. So substances which only have dispersion forces tend to have lower boiling points. Why? Because in order for a liquid to boil, what is happening is the intermolecular forces need to be overcome. That liquid needs to gain on a particle basis enough kinetic energy for the liquid molecules to gain enough degrees of freedom and escape into the gaseous state. So other kinds of intermolecular attractions are dipole-dipole interactions. So between permanent dipoles. Permanent dipoles exist due to polar bonds, right? So when you've got an electronegativity difference, then you get a permanent bond dipole, a delta minus, delta plus, not a full charge separation, okay? And one subset of dipole-dipole interactions is hydrogen bonding interactions. Hydrogen bonding interactions are stronger than your average dipole-dipole interactions, and those occur between oxygen-hydrogen, nitrogen-hydrogen, and fluorine-hydrogen bonds, because those bonds in particular are so electronegative, such strong electronegativity, okay? So those are going to result in higher boiling points than normal dipole-dipole interactions, which is why the boiling point for water is actually much higher than other group 16 hydrides. Okay, so if we were going to look at these substances that we have here, we've got two elements, iron and helium. An element is only going to have dispersion forces. Out of the two of these, iron is going to have a higher boiling point than helium because it has more electrons than helium. So it looks like helium is going to be the bottom of the pile here. And then we've got these two compounds here with very similar molar masses, right? Carbon's about 12, hydrogen's about 1, so 12 plus 12 plus 1 plus 1. It's going to be about 26, and that is the same here. 12 plus 14 plus 1. It's going to be very similar magnitude in terms of mass, so similar dispersion forces. However, substance C, we see no bond dipoles, right? Carbon-hydrogen bond, non-polar, carbon-carbon bond, non-polar, okay? So again, this is going to be dispersion forces only, with a higher molar mass than iron, okay? So again, dispersion only, but the carbon-nitrogen bond is going to have a dipole moment associated with it, okay? So the nitrogen is going to be my delta minus end, and my carbon is going to be my delta plus end. Not a hydrogen bond, just a normal dipole-dipole interaction. So if I had another species here that had like a nitrogen-hydrogen bond, for example, that would have a higher boiling point. So to rank these then, helium is going to have the lowest boiling point, so that's going to be my number 4. And then iron's going to be my next lowest, and then my next lowest, and my highest boiling point would be this one. Okay, so hopefully that is helpful. I'm going to see if I can actually generate another question, or if it's not going to be very helpful to me here. Here we actually have some pictures, okay? So there's a few different ways this question can be asked. So what you are looking out for, I'm sorry, I can't see this very well. For instance, here, substance A, we should be able to point out, oh, we've got a really nice delta minus, delta plus bond dipole here. Not only that, that fits our criteria for hydrogen bonding. So I'm going to expect that to have a super high boiling point compared to anything else. In here, we also have a polar bond, okay? So we have a delta minus, delta plus, but it is not a hydrogen bond. So the oxygen's delta minus, the carbons on either side are delta plus. So this is dipole-dipole. but not hydrogen bonding. So it's still going to result in an elevated boiling point compared to dispersion-only forces, but not to as great a state as hydrogen bonding. And then we have chromium and argon, both elements, so dispersion forces only. You might have to actually look these up in the periodic table. So chromium has Z of 24 and argon has Z of 18. So the dispersion forces in chromium are going to be higher than the dispersion forces in argon. So if we're going to put all this together, then our lowest boiling point is going to be number 4, so that will be argon. Our next lowest boiling point will be krypton, and then dipole-dipole interactions will be next, and our highest boiling point will be substance A because that has hydrogen bonding as well.